Okay, so second last lesson for gas laws. We're going to look at manipulating these three variables and the relationship between them. So when we are talking about gases, when you have pressure, we're talking about how often or how much force particles use to collide with the side of the container. That's how we will measure gas pressure. Volume is how much space will take up, and then temperature again is the a measure of how fast the particles are moving. And the good thing with this is, like I said in the first lesson, a lot of these laws, you can think about it logically, and even if you don't remember the formula, it actually makes a lot of sense. Okay, so Boyle, Robert Boyle, he actually did a bunch of things. He even worked with plants and oxygen, but it was still all surrounding gases, really. And Boyle said that, or discovered that, when you have a change in pressure, then that is going to have an inverse effect on volume, or vice versa. So this really little simple picture here is you have a container and it says volume is 1 liter. And then when you decrease the volume, say by half, then that is going to actually make the pressure increase. So it's an inverse or opposite relationship, which makes a lot of sense. If you decrease the amount of volume that gas will take up, then those particles are going to collide with the sides of the container more often. And then, of course, this colliding with the side of the container, that's how gas pressure is measured. Okay? So this is the math formula here. P1V1 equals P2V2. And so we have a sample of helium gas collected at standard temperature in a 4.5 liter balloon at STP, which is standard temperature and pressure. The balloon is then submerged in a tub of water, also at standard temperature, such that the external pressure is increased to 110.2 kPa. What will the final volume of the balloon be? So when you do the first three laws, if you printed the note off, the first three laws, they're only looking at two variables: what happens with pressure, volume, what happens with pressure, temperature, and what happens with volume and temperature. And then logically, they all sort of kind of go together. So you can also do a combined gas law as well. Okay, so here we have, it says standard temperature, and then again, standard temperature. So that means that temperature is constant, and only pressure and volume are changing. Okay, so we have a 4.5 liter balloon at STP. So standard pressure is 101.3 kPa, which is our initial pressure. And then the pressure is changing to 110.2 kPa. And it asks us, what will the final volume be? So you want to make sure that the units match. So there was that pressure conversion ratio we did in the first lesson that you might need to use depending on what the question says. Okay, so but here we got kPa, and then our volume. If the initial volume's in liters, might as well leave the second volume in liters. It doesn't ask us to change it to milliliters, so why not? So P1, 101.3 kPa, V1, P2, 110.2 kPa, V2. So V2 is going to be Okay, so then the kPAs cancel out and you're left with liters. And our answer is, so even before you do the answer, when you're increasing the pressure, so then according to the relationship, that means that the volume needs to decrease. So even before you get an answer, you can think logically about what you should get. So it should be less than 4.15. Sorry, 4.5. And the answer is 4.14, which is less. So that makes sense. Okay, so the next law is Charles, and Charles did experiments with volume and temperature. So using a glass syringe, a scientist draws exactly 25.5 centimeters cubed. Centimeters cubed, if you don't remember from grade 9 math, is a unit for volume. So again, it doesn't really matter. We just have to make sure it matches. Of dry oxygen at 20 degrees Celsius from a metal cylinder. She needs to heat the oxygen for an experiment, so she places the syringe in an oven at 65 degrees Celsius and leaves it there for 30 minutes. Assuming the atmospheric pressure remains the same, so again, pressure is constant, what volume will the oxygen occupy? So again, we're looking for volume. And this time we have two different temperatures. So because we are basically all the formulas, you're multiplying and dividing, and whether it's 2 variables or 3 variables or 4 variables. And so because degrees Celsius can, when you get into the negative side, like below 0, that means cold. That negative number, first of all, if you divide a positive number by a negative number, your answer is negative, right? Or multiply. So what can happen is, even though temperature can be negative, then you might get a negative volume, which scientifically does not make any sense. Also, because it's not a continuum of temperature, then what can happen is it can also mess up trying to figure out what the law should have done. So the relationship. So if temperature increases, what should happen to volume? When you have a negative number, increasing negative is actually more negative, right? So the science and the math don't mesh well. However, if we use Kelvin, so the Kelvin scale starts at absolute 0 or 0 Kelvin, there is no negative numbers. You can't go below absolute 0, right? Life can't exist. So then changing the answer to Kelvin, or the temperature to Kelvin, is going to ensure that the relationships are valid, and mathematically and scientifically, and that you're not going to get a weird answer like a negative volume or whatever. So you have to change your answer. Sorry, you have to change your temperatures into Kelvin. That's supposed to be a capital K. And the good news is, if you're the kind of person who likes to check your answer in the back of the book, if you do the homework and you don't change it to Kelvin, you'll get an answer. Like, unless it's, maybe a weird negative situation, you'll get an answer, but it will match with what it says in the book. So again, you must change your degrees Celsius into Kelvin. Okay. And to do that, if you forget from the first lesson, Kelvin is degrees Celsius plus 273. And that has to do with the mathematical prediction of when absolute 0 occurs at negative 273 degrees Celsius. Okay, so the first volume is 25.5 centimeters cubed. And because we're looking for the second volume, then it actually, we can just leave it as centimeters cubed. You don't have to worry about converting it. But then the temperature, we want to change into Kelvin. Just by adding 273, no problem. Okay, so now we have our values. So the 25 centimeters cubed of oxygen at 293 Kelvin now. And what will the new volume be when we increase the temperature? So again, you can think about how this is related. If you make particles warmer, then they are going to go faster, which means they are going to take up more space. So here in this picture, it's a hot air balloon. So the balloon just captures the gas, but you can see the fire there. So the hot air is making the gas particles much warmer, and then they are increasing their volume, taking up more space. The balloon expands and rises, and you can beautiful sightseeing tour, whatever. Okay, so here we have an increase from 20 to 65 degrees, or 293 to 338 Kelvin. It actually doesn't matter in this case which one you consider. That's quite a huge temperature change. So that means that means that our volume should increase as well. Okay. So now you can decide how you want to solve for this. So you can still use like cross multiplying. You can do 25.5 divided by 293 and then times 338. There's a variety of ways you can think of it. Oh, and I didn't write my units in for those of you that like dimensional analysis. So then V2 is going to be 25.5 centimeters cubed times 338 Kelvin divided by 293 Kelvin. Cross that out. So the second volume is 29.4 centimeters cubed. So bigger than 25.5 because the temperature increased. Okay. All right, so then Gay-Lussac's law is with pressure and temperature. So again, we're still going to change the temperature into Kelvin. And again, this one is logical. So if you increase the temperature, then particles are moving faster. So then is it logical if they're moving faster that they're going to collide with the container more often? Yes. So this picture here tries to use, this is a common thing. So these arrows are trying to show particle movement. Okay, so these are small arrows. And then on this side, you can see this picture of a Bunsen burner here increasing the temperature. And you can see now they've tried to use bigger arrows to show the particles are moving more often, and then logically that means they're going to hit the sides of the container more often and with more force, which has increased the pressure. So this clock-like thing is a pressure gauge. Okay. So a cylinder of chlorine gas is stored in a concrete-lined room for safety. The cylinder is designed to withstand 50 atmospheres of pressure. The pressure gauge reads 35 atmospheres at 23.2 degrees Celsius. An accidental fire in the room next door causes the temperature in the storage room to increase to 87.5 degrees Celsius. What would the pressure gauge read at this temperature, and would the cylinder explode? So similar to the Billy and Sally and the nitrates in his water, this value here, this is the limit. So we actually don't need to do any calculations with this, or you could go backwards and see what it would be, but you don't have to. We're going to use the initial pressure, which is 35 atmospheres, and the initial temperature is 23.2. You can right away add 273 to that, always changing it to Kelvin. And then the second pressure, we don't know what it's going to be, but we want to see, is it less than 50 atmospheres? And if it's less, then we're good. If it's not, then that is not okay. So those of you that continue on in manufacturing or engineering, then these are the kind of situations that, depending on what kind of job you have, you might have to consider, like what are the safety limits, whatever you're talking about, the strength of a material, any of that kind of stuff. Is the pressure going to be too much? These are the kinds of things that you actually might have to calculate. Okay, so pressure and temperature, they are a direct relationship similar to volume and temperature. When the temperature goes up, so does the pressure. And again, we can leave it in atmospheres. There's no indication. It doesn't say in the question we have to change it to kPa or torr or anything like that. We'll just leave it as atmospheres. I wrote 2 instead of 3, sorry. Okay, and again, decide how you want to solve this. Sorry, I'm going to put 2 equal signs on a line. You get 35 times 360.5 divided by 296.2 is 42.6. And then the K's cancel and you're left with ATM. Okay, and then just remember, in this kind of question, you just have to make sure you answer it. So we found the value. Now you look and say, would the cylinder explode? Therefore, the cylinder would not explode. Because 42.6 ATMs is less than the limit of 50. Okay, so that is a complete answer. Okay, so maybe even in this scenario here, when you look at this one's actually better. If you think about the hot air balloon, if you warm up the particles, the gas particles, then they are going to move faster, which means they're going to hit the sides of the container more often, increasing the temperature. But they're also going to expand their space, right? The balloon expands because the gas's volume is also expanding. So there are many situations where you need the combined gas law, P1 V1 over T1, P2 V2 over T2. So essentially this is, sorry, I just got rid of it. This is all of the gas laws together. Block out the temperature, you have Boyle's law. Block out the pressure, you have Charles's law. Block out the volume and you get Gay-Lussac's law. So we've just put them all together in a situation where you're given information about all of the variables. So Billy the chemistry superstar is having a party to celebrate Mole Day, which is a thing. It's October 23rd, 1023, like Avogadro's number. The day of the party, the atmospheric conditions in the morning were -2 degrees Celsius and 100.8 kPa. Okay, so we've got, you can write it down as you go. So here, this is an issue, right? If you've got -2, that's bad because we don't want to end up with a negative volume, okay? P1 is 108 kPa. And V1, we don't know yet. A cold front moves in and the conditions change to 103 kPa and -25 degrees Celsius. Oops. Okay, so this is where it would screw up, right? The lower the temperature, then here, like -2 and -25. -25 is a colder temperature, but it's not a lower value, right, on the negative side. So mathematically and scientifically, changing it to Kelvin is going to make it work out better. What would happen to the volume of the 4.2 liter balloons tied to the front of the house? So initially, their volume is 4.2 liters, and we are going to solve for the second volume. So this maybe is a lot of, this is too much if you want, so you can just do the math, like 100.8 kPa times 4.2 divided by 271 gets you 15.622. 103 divided by 248. But you can still do, you could do cross multiplying with all of it if you wanted to. So then what cancels out? So we would be, the kPa cancel, the K cancel, we would be left with liters. If you have an answer button on your calculator, this can also be a case where that is going to help you out. I have the wrong decimal place here. I was going to say. Sorry, this should be 1.5622. So 3.76 liters. Okay, so our balloons went down in volume because the temperature decreased. Okay, so again, you're now, and the pressure increased, right? So that's an inverse relationship. So now when you change it to Kelvin, then scientifically the relationships work as well as mathematically. We don't want a negative volume. Okay. So Dalton, like the Dalton who proposed the four postulates in one of the early atomic theories, he did, and most early scientists used gases because they were easy to manipulate and easy to get. So he described, or he developed the Dalton's law of partial pressures. So, and it's actually a very straightforward law. It's sort of intuitive, really. If you have a mixture of gases, then the total pressure is going to be the sum of each individual gas. So the pressure of gas number 1 plus the pressure of gas number 2 plus the pressure of gas number whatever, okay? As many as you have. So their total pressure added together is going to equal the total in the container. So this question says, a mixture of nitrogen and carbon dioxide gases, so here we only have 2, is at a pressure of 1 atmosphere and a temperature of 278 Kelvin. So that 278 Kelvin we actually don't even need in this question. The law of partial pressures is so simple. If 30% of the mixture is nitrogen, what is the partial pressure of the carbon dioxide? So we have some of you, if you are good with math and percentages, then 30% of 1, you might recognize that that's 0.3. If you forget how to do percentages, so the pressure of nitrogen gas is 30% of 1. So when you do 30%, that's like 30 over 100, and then you multiply by the value, which is 0.3. So we have the total. and we have the pressure of nitrogen gas, and we are asked to find the carbon dioxide. So then you're just subtracting. Okay. And you can check your answer. 0.7 plus 0.3 equals 1. So this formula is really straightforward. Okay, the last thing that you could have to consider is collecting gas over water. So this, if you look at the picture here, this is where, this is displacement. And this is actually a pretty simple experiment to do. So in elementary school, you might have actually done this. So you can use any sort of reaction that produces a gas. So you could put vinegar and baking soda together, and then you just have to, so this is a stopper. And what you want is the gas to travel in this tube here. And then the water, you fill a test tube with water. So initially the water would be all the way right at the top. And then as the gas bubbles in, then the water comes out, and then you can measure how much gas is collected. So you can measure the milliliters of the gas. You can also measure the pressure. So when you have gas collected over a container of water, it's a mixture. So it will apply, you can apply Dalton's law of partial pressures to it. So if the mixture is warm, it collects a greater percentage of water vapor. So the partial pressure of water depends on temperature. So you need this table here in order to get the pressure of the water vapor at a particular temperature. Like that would have to be given to you, okay? And the partial pressure of water vapor in a gas mixture is known as, it's called the vapor pressure. And all we're doing is applying Dalton's law of partial pressures to collecting gas over water. So we are going to add the pressure of the gas collected plus the pressure of the water vapor equals the atmospheric pressure. Okay, so hydrogen gas is collected using a downward water displacement. If the atmospheric pressure is 100.5 kPa, and the temperature is 20 degrees Celsius, determine the pressure of the hydrogen gas. So we need this, and go to page 596, table number 1. Or to be honest, you could probably Google it. And at 20 degrees Celsius, the pressure of the water vapor is 2.34. Okay, that's not a ton, but remember, as you move forward in chemistry, we're always trying to be more analytical, right? More quantitative. So the better your numbers are, then the less mistakes are made. So the atmospheric pressure equals the gas collected, which in our case is hydrogen, plus the pressure of the water vapor. So this looks really similar to Dalton's law of partial pressures, right? So we have 100.5 kPa. We don't know hydrogens. I can't even spell gas. We don't know hydrogen's pressure. Oh, we do know that one, sorry. So again, to get the pressure of hydrogen, you're just doing 100.5 minus 2.34. Those are both kPa. Okay, pretty straightforward. Okay, so there is quite a list of questions for homework. So the they're sort of divided by law. Okay, so don't just do all of the first set and think, oh, I'm good. If you are rushed for time, then do like one of each set so that you get experience with each of the laws. Okay, thank you.